So I'm very happy to have John Bentley visiting us today. There's quite a crowd, well, it seems to be occupying a fair chunk of the front row here, of people that used to occupy the Unix room back at Bell Labs. So in the olden days, there was one Bell system, and it worked. And a lot of us were sitting in this place in Murray Hill. And over time, more and more people have come to Google. So now it feels like this has become sort of the home base for a lot of us. So we're really glad that John joined us. Over the years, that Bell Labs split into a bunch of pieces. One of those is Avaya Labs. That's the part of Bell Labs that split off that kind of owns the enterprise telephone systems. And I guess this campus uses Avaya products, so good. John has done a lot of great things over the years in computer science, right? I first started reading about his papers, probably back in graduate school, right, with searching in space and so forth. And one of the big things he's made a name for himself for at Bell Labs was coming up with little languages that could quickly allow people to express solutions to problems. He'd worked a lot with Doug McElroy on various things, and I believe that's the topic of today's talk. So, further ado, John.
Eric was being particularly gracious about describing Avaya as enterprise communications. When I chose to go to Avaya, Bjarne Straustrup said, "Oh, you're going to Ravi Sethi's PBX research lab." So, we have some other alumni of the PBX Research Lab here, but I won't disgrace Tom in that particular way. So today I want to tell you about beauty. It's sort of audacious to do this, but there's a reasonably cool book. You said you spent this morning looking at the book? Is it reasonably cool? Is reasonably cool an okay description? Yeah. But I think it's sort of a really neat idea of a book called Beautiful Code, and you get a few dozen people to talk about what's the most beautiful code you've ever written. I'm here unabashedly to talk about the book, and the only reason I don't feel really even more shame than I should, well, apart from being raised wrong, is the fact that all profits are going to an organization, and an organization that I, as a guy who goes on wearing West Point t-shirts, am not all that fond of. So it's I have no private monetary axe to grind here. A delicious question. What's the most beautiful code you've ever written? Got email out of the blue. Do I want to write a chapter for this book about the most beautiful code I've ever written? Think about that. And it was delicious. It rolled around in my brain for the better part of the day. A beautiful code, well, maybe you mean what's the simplest, cleanest, smallest implementation of a function that most people make pretty big and ugly. That's beauty. Maybe forget this beauty for its own sake, maybe for a real production code. What's the most beautiful piece of production code that's been widely used that you've written? And finally, the one that really intrigued me is, what's the most beautiful piece of code you never wrote? I once heard a colleague of ours praise someone ultimately as, quote, he adds function by deleting code. And how can I talk about that? And that's really, in a certain sense, the most beautiful. So I thought about these three things for about a day, and I realized that my answer to each one of them was Quicksort. That I had three different versions of Quicksort. And so, in fact, in the book, chapter 3 is called The Most Beautiful Code I Never Wrote, and is about this. But what I want to do today is that if you want to look at the book, it's available. It's, I think, sort of neat. But I'm going to tell you the bigger story. So in the second section, I sort of just very briefly survey that, but it's fun to tell you the bigger story, and that's what I want to do. So I'm going to talk first about a really elegant, tiny implementation of Quicksort. Then I'm going to tell you the story of analyzing the runtime of Quicksort, where we'll start with number 1, instrument it for a long time, then transform it, where each one we'll go through a series of about a dozen different programs. Each one is a very simple change from the previous one. You start off with a dozen lines of code, and finally, poof, it disappears into a puff of mathematical smoke, and all you have left is a mathematical analysis. So that's going to be the third thing. And finally, a production Qsort that I wrote with Doug McElroy. The first two are admittedly only Fabergé eggs. They're tiny, beautiful, deliciously crafted small objects that really have not much real-world use. The third thing really is real-world code, but it's still on the small side. So everything I'm going to talk about here is smallish, but some of it is semi-real. If I say Quicksort, just to make me feel better, or not, who feels, yeah, I know the Quicksort algorithm? Oh, this is so cool. It's the classic divide and conquer algorithm. To sort the array, you choose the first element, partition around it, so everything over here is littler, everything over there is bigger, the first element is right there. So you've divided it, now you conquer by recursively sorting both subarrays. A really simple, delightful, easy algorithm. In the very best case, how much time does it take? Well, in the very best case, you get lucky. Computer programmers are optimists. Well, I think things going to happen. I split it in the middle. I get a recurrence that t of n equals twice t of n over 2 plus O of n. Solution is n log n. It takes n log n time, which is optimal for sorting. You can't do much better than that. In the worst case, however, and every computer programmer who's ever written at least one program knows that this often happens, I only peel off one element at a time, and therefore the algorithm takes n squared time. So best case, worst case. On the average, well, I just add them up and divide by 2? Well, not really. It's really n log n and fast 2. I'll give you the details soon. So it's a pretty reasonable algorithm. How exactly, so the idea of Quicksort's really easy, but how exactly do I partition the elements of an array around a given element such that littler ones are on this side, bigger ones are on that side? And exactly what happens to the equal elements? What do I do with that? It's conceptually straightforward. There were a couple ugly days in the summer of 1975 when I took a Quicksort right out of a classic algorithms book. Now, at the time, it wasn't Knuth's, and I wouldn't badmouth Aho, Hawcroft, and Ullman because they're friends. But I took it out of some unnamed algorithms book. And I spent a couple days debugging it. I didn't look there because I knew I had that code right out of the book. It was correct, but it wasn't. So it was a couple days of debugging made it tough. I'll give you the details shortly. But here's what the code looks like. Many of you, I think most of you have seen code like this, where you run one pointer up, the other pointer comes down, the descriptions go like this and like that, then you swap them and keep on going. So that's the code. That looks like pretty reasonable code. It's not that long, a tad over a dozen lines. But I realize that it's more than the likes of my little brain can understand, that I was able to look at code like this and get it wrong for a couple nasty days of debugging. I think the reason is that whenever you have a dual while construct, whenever you sort of set things up so that I do the option first, I do the operation first, and something else happens, it's sort of hard to understand. But this is the code. It's not that subtle. I'm not going to describe this one in detail, but I want to get it simpler. So what I'm going to do is I'm going to tell you about one classic technique, randomization. If a problem is too hard, toss a coin to weasel your way around it. In Quicksort, what I could do is, it works really well on the average, but if I happen to have elements that are already sorted, each time I'll choose the first element, I'll partition it, does nothing, I only plot off one element, I keep on going one by one by one. Horrible. If I shuffle the whole input before the run, that gets around that problem. Even more easily, this is from Hoare's 62 paper, if I just randomly choose a partition element with that much code, I can let the randomization apply the expected analyses to input from your worst enemy. That's pretty cool. Here's the partitioning. When teaching, I really had trouble explaining the code I just showed you. While coding, I always had to use my own trusted version. I couldn't just sit down and type out the lines of code. I didn't really understand it. I wanted to find an algorithm so simple that I could understand it, code it, and explain it. And I was reviewing a paper by a guy named Nicola Muto, who had a really clever algorithm for a related problem. And we'll use this loop invariant, which says that rather than having these two pointers, I'll just have one pointer. And this this is so cool. So here, if I want to sort the array from L to U, I'll let the middle value M fall in the middle. I'll let the current index I be right here. The invariant is that this is the partition value t, everything over here is less than t, everything over there is greater than or equal to t. Well, if I come here, what do I do now? Well, if it's greater than t, what do I do? It's pretty easy, just leave it alone. If it's equal to t, I leave it alone. But how can I maintain this invariant if it's less than t? Well, that's also pretty easy. I can just swap it back to here, put this one up there, and continue. So if if I do that at the end of this operation, I'll have the array that looks like this. I now just swap T from here into position M, and I can recursively sort from L to M minus 1, from M plus 1 to U. That's a really simple partitioning scheme. It's sort of important to understand this. I'm going to stop right now. Who thinks that they really understand this dead cold already? Who has any questions? If you have any questions at all, please ask. It's really, yeah.
Are we assuming all elements are distinct?
No. So here, all you're assuming is that the elements are totally ordered, that there's some comparison function you can call, and it will be either it's littler, it's bigger, or it's the same as. So all I'm assuming is a total order. Okay, so here that's pretty easy code. In fact, now here's the algorithm. M is L for I gets L plus 1 up to U, increment it. If x sub I is less than x to t, only if it's strictly less than, swap it, increment M and I. Really pretty simple stuff. This is my first claim that code that might be close to beautiful. It's a really simple little quicksort, and this is beautiful only in the sense of taking an algorithm that when I first saw it was presented as 30 lines of code. When I first studied it in Knuth, it was presented as 50 lines of mixed code, and really it doesn't need to make all that much a deal out of it. If L is greater than U, I want to sort from L to U. Well, I'm done by definition. Otherwise, take the loop we saw before, swap it at the end, then recursively call it from L to M minus 1, from M plus 1 to U. So a really pretty simple code. Yes?
If all elements are the same, it's still n squared.
Pardon me?
If all elements are the same, it's still n squared, isn't it?
If all elements are the same, it's still n squared. And that is going to come back and bite us on the butt repeatedly. But fortunately, on this next slide, I say right here, it's quadratic time for increasing elements. Randomization fixes that. It's quadratic time for equal elements. Is there a beautiful solution to that problem? So you foresaw, this one is only a factor of 2. What's a factor of 2 among friends? No, we don't care about that, really. This one is quadratic, but here we can fix it. This one we can't fix. So you honed right in on the major weakness. I think sort of an interesting open problem is there a beautiful code that fixes this particular problem? This doesn't fix that problem. I have some ideas about that. I'll be happy to talk to people afterwards only on maybe adding 3 or 4 lines of code to fix that. I think it might work, might go. Other questions? Great question, thank you. Yes?
Another weakness is that it's not stable, isn't it?
It's not stable, and essentially, one really nice property of a sort is that you leave elements you leave equal elements in the order in which they appeared. Things like merge sort have that property. It's really a delightful property for many things. You can gain that property by adding on fictitious numbers, but this one is not stable. Picky. I mean, geez. Any other whines? Okay. So like I said, its strengths are numerous. It's simple to explain, it's simple to code. It happens to be correct. I'm pretty sure that's, I'm a clever lad, but getting the bug into that much code is hard even for me. It's pretty fast. Prasado's a master, he knows that he could do it. It makes experimenting easy. Strunk and White admonish us that vigorous writing is concise, omit needless words. It's a real joy to take a program and to try to make it as small as possible, try to just cut things down to its essence. And again, there are these weaknesses. Other questions?
Yeah.
Oh.
Suppose the number of elements are so large that the array doesn't fit on one machine. I suppose it takes 10,000 machines to store your array. Now what?
Wait. Let me see where I am. Oh, Google. Okay, yeah. That's a really interesting question, but it's beyond what I want to talk about today. No problem is so large that it can't be run away from. It's an interesting question, but beyond the scope for today. So here might be the simplest semi-production C quicksort. Just the previous code before where I add in the swap And this is a pretty useful code. It's not silly. That's point number one, tiny little code. Point number two is how much time do it take? Before I gave you the worst case, the best case, how about the expected runtime? On the average, how much time does it take? And here I'm going to say, let's do expected first only on indistinct elements. I'll come back shortly in about 20 minutes to what happens if we have equal elements. I'll get to that again, but for the time being, just help me out here with the issue of how much time will this take on a set of indistinct elements? Well, firstly, what do I count? Do I count the nanoseconds on a particular machine? Well, that's really useful if you want to do real engineering. Do I count some critical operations? Do I count the number of comparisons? Do I count the number of swaps? Whatever. How do I count it? Do I do experiments? Do I do mathematics? Do I combine it? All those are difficult questions. How do I graph the output? Well, if I graph size here and runtime here, what will the graph look like with n here and runtime there? It'll be sort of a line, roughly. What's a better graph than just time versus runtime? Well, one thing that I might do, if I put the runtime divided by n over here in a linear scale, and if I have n on a log scale there, that'll show me the time per element. And if it's an n log n algorithm, how should that grow? So if I do a real graph of real runtime, what will this thing look like? Well, you might hope that it will be a line. Will it be a line? What will it be? I'm getting towards your question, and that is that if I measure real runs, plot averages of many runs with nanoseconds divided by n, and I do it for first Quicksort and then for a heap sort, I see curves like that. Why do I see curves like that? These are lines. I mean, these all are straight, except they're straight at 3 different angles. Yeah. So I'm tickling at the other end of the question you asked. Where do these, so here, this one is linear up to about where at the first place? What number? Yeah, at about 8,000 4-byte integers, about 32 kilobytes for the L1 cache. Here up to 512 kilobytes for the L2 cache, and then here RAM. So here, for heap sort, it really runs around memory. It bounces all over. It's not a particularly cache-friendly algorithm. Therefore, you see 3 different domains. Heap sort's a much more cache-friendly algorithm, even though here you can see that. There are still 3 different domains there. So, and sometimes something else happened on my machine where my machine burped in the middle of the experiment, and this happens. So you can look at real runtimes. If you do that, it's a bit delicate. Runtimes are interesting. Interesting is sometimes interesting. What I can do instead is I'll count key operations. That'll be much more mathematically smooth. I could count the number of swaps. I'll instead count the number of compares, because before I do any swap, I'll do a compare. So that's what I'll do. So what I can do now is I can take this program that we had before and just add the statement to it. Initially, comps is equal to 0. Afterwards, I'll print out the number of comparisons. And here, right before I do any comparison, I'll add in 1 line of code. So I'm going to take this program, add in 1 line of code, and instrument it, and go from there. If I run this program now, I'll be able to get a graph where I can see the number of comparisons as a function of that, and the number of comparisons divided by n if I want to. A pretty interesting graph. But am I ready to run this program yet? Is there anything I can do to make it a little bit faster, a little bit cooler before I run the program? What can I do to make this program cooler before I run it?
That's with the array.
We'll get right there. So I'm going to do a series of transformations. A designer knows he's achieved perfection not when there's nothing left to add, but when there's nothing left to take away. In software, the most beautiful code, the most beautiful functions, the most beautiful programs aren't there at all sometimes. Fasten your seatbelt. I'm going to go through a sequence of a dozen versions of this right now. There is no test at the end about this, so you can weasel out of that one. But the first thing I can do is, rather than having to count right in there, I can put this up here. And I can't get rid of the array until I do this. It's a great thing. So the first thing I can do is that, just move the comparisons out to make it a bit easier. But now I can take the advice of dispense with the array. That's a quote. Why can't I dispense with the, I'm sorting. I have to sort something, don't I? Well, no, I don't. I don't really have to sort anything. What I can do is I can take the program and run it. What I'm running now is not, I start off by running the sort program. Next I'm going to run a program that just models a sort program. A sort program sorts. This model program is going to be a schema that does the same action that the sort program would have, but it won't bother sorting the array. Well, if I don't have the array, what can I get rid of here? If I don't have the array, I don't have to do all this nonsense of swapping. If I don't have the array, I don't have to do that swap. I can get rid of the integer I. And instead of saying that swap with a random partition element, just assign the middle value to be some random element. Because I'm going to swap, and again, I've assumed here that these are all indistinct elements. So if I swap all this, I just get down to this schema program that looks roughly like this. And I can now simplify this just to be the skeleton program, to be a quicksort count. If L is greater than U, return. Otherwise, you partition around this. That's your middle element. The comparisons are incremented by that and recur both ways here. Everyone get that idea? So I'm going from a program that really sorts to a program that is over here modeling a sort that on average will have exactly the same stochastic behavior.
But you're only able to do that because your algorithm is not dependent on the data.
It's not dependent on the data in certain senses, yes. So here I'm going to accurately count the number of comparisons I'm making. Am I going to count the number of swaps I'm making? No.
I think rephrase what he says, I think there's an implicit assumption that the randomness in the random function mimics the distribution of the real data as you sort.
Yeah, and again, that assumption is clear that if I have God's own random number generator here, it gives me that, then it's easy to prove that on the average, I'm equally likely to choose any particular notion here. So you can't do this everywhere. You can do this in a surprising number of places. I chose this example that the first time I really did this was an analysis of a traveling salesman program where I wanted to do a strip heuristic where you sort of go inside this strip and come down that strip and go back and forth for planar points. And I realized that I could generate all the points at once and do that, or I could just consider the points in the strip, and then I could say, well, how far up is the next point? How far over is the next point? And all these were very easy distributions. And I found a way to get down from 100 lines of code to about a dozen lines of code, and then I found that those bastards, Beardwood, Halton, and Hammersley, in the Proceedings of the Cambridge Philosophical Society, sluts, in 1957 had done the same thing. And they reduced it to a double integral. But this sort of thing happens. I'm cheating, but it's a general trick. You can cheat in a lot of places. You know, Newton didn't really look at the planets. He just had this little model for the planets. Bastard, I say. So what that does is it reduces the time from n log n down to linear, and it reduces the space from linear to log n. So again, I'm cheating here. I'm only doing a model. I'm not really having planets go around the sun. I'm having this model of, what if an inverse squared law? So Pascal famously said, if I had had more time, I would have written you a shorter letter. We have the time. Is it possible to shorten this letter? Well, that's pretty natural. Do I really need the L and the U now? Well, I can replace two indices with one length. So just choose the length here. If n is less than one, return. Otherwise, it's a random integer. Do that one and that one. That's pretty nice. But do I really need to make it a function or to make it essentially a procedure, a void? I can just do an integer comparison count, where here I say if n is less than 1, return 0. Otherwise, it's a random int and return this thing. So here I've gotten down from this dozen-line program to about a 4 or 5-line program that does the same thing. I hope that this is pretty clear so far. Next step is going to be difficult. We started off by a real program that really sorts. We went next to a skeleton program. I'm going to now do a model of the program. Polya admonishes us that the inventor's paradox says that sometimes the more ambitious plan may have more chance of success. Suppose that we don't want to do one experiment, but I want to find the true average. What would that program look like? So I wanted to make the goal of computing not just one experiment's worth, but the true average number of comparisons, assuming that all partitions are clearly likely. Here's a pseudocode. To do the C of n, if n is less than 1, return 0. Otherwise, compute the average. Let every single partition element be chosen. And again, this is just making a statement. For the partitioning element from 1 up to n, that can be the one you choose, the sum is that, and return the sum divided by n. So here I'm taking the same outline as before, but now I'm adding it all up, dividing it by n to do the average. It's really cool. It's a much more interesting answer. Now instead of having to run a bunch of experiments, I just get one true answer. Unfortunately, I'm computing the same answer over and over and over again recursively, and that makes it exponential. Sucks to be John in so many ways. But is there a trick that anyone here knows for if you do the same answer over and over and over again? Yeah.
So you're dividing by n, so the sum is summing a number plus an integer plus two floats, which are not on the same scale.
Yeah, no, this is, I should have said 0.0. My bad.
No, the c, the n minus 1 is the number, and the others are other.
Yes. And again, there's not going to be a test at the end. There's some subtle stuff going on here. I'm going to just sort of zoom along. If you understand it, fine. If not, I think you'll appreciate it anyway, just to see where we go at the end. But it's subtle. I could easily spend the whole hour just talking about the details of this, but there's other cool stuff to talk about. So here I compute the same thing over and over again. It's exponential. What's the magic technique we have to solve that problem? Memoize. See? It shows the benefits of a bad education, that you came from this nasty Lisp background in your kindergarten, and dynamic program, you hung out with proper OR people. So you were raised appropriately, because on the next slide, slide after this. So here we have the real deal, we have an instrumented program, we have a skeleton program, and now we have a model of this. So how you rhythm up behavior, and how do I make it faster? Dynamic programming. So I just spelled memoize funny. So I didn't go to MIT, so I can't spell memoize. A really trivial example of dynamic programming, let T of n store C of n, compute in increasing order. To compute this up to the value capital N, for every n being the program size up to some maximum capital N, just do this. Just do the table access. So I'm just going to do that by converting this function into a table and computing it in increasing order. Pretty cool. Are we done? Ready to run the program? Nah. Right now, it looks like this. What I can do instead is move this n minus 1 out of the loop. That's pretty easy. This becomes the inner loop. Can I make that loop at all faster? This nasty inner loop? This is the inner loop now. Can I make it at all faster? I'm adding up, if n is 5, well, we'll see it. So the inner loop is like this originally. It adds up t of 1 plus t of 3, if n equals 4. T of 1 plus t of 2, t of 2 plus t of 1, t of 3 plus t of 0. Notice this is the same as, I'm just adding things up this way and that is coming from the, it's so much easier, it's so much cleaner to write it as twice this. So here I'll take that loop and replace it with that loop. Pretty obvious. Currently I have quadratic code, where in the inner loop, every time I add up this loop. But what changes? I add a t of 1 plus t of 2 plus t of 3 plus t of 4 plus t of 519 plus t of 520. Well, all the change from last time is the last element. So I can change this by not recomputing the initial terms and just add in the last element here. Ooh. So now this is my new complete loop. I've taken it from quadratic time from capital N squared down to capital N. So currently, I've got a pretty small piece of code, about 4 lines of code, that gives me much, much more than I got before. And if I continue with this, can I make it any better than that? Space, the final frontier. I can remove t to compute c of n in this much time and space just by saying that rather than making t the table of elements, only compute the last element. And if I do that, this becomes the final code. So it's just essentially a recurrence relation, a system of recurrence relations of two equations and two variables. And if I want to now, I can turn this pretty much into mathematics. Perlis, as one of his many wonderful Perlisisms, observed that simplicity does not precede complexity often, but follows it. So I started off in version 1 of how 13 lines of code can give you one answer in n log n time. By the final one, I have 4 lines of code that instead of giving you a sample, give you an exact answer. I can compute all n answers in capital N time and constant space. In fact, I can sort of review this or rephrase this as this recurrence relation that many of you who studied the Quicksort paper and its descendants, and if you have studied the Quicksort at all, you've studied the Quicksort paper and Knuth's description of it. We can go to this recurrence. Every one of the mathematical tricks that you may have been tortured by in class, in fact, corresponds to a code trick we just saw. That one of the real cool things about talking about this to undergraduates is you ask how many people love coding. Oh, we all love code. How many people like mathematics? Boo, math is bad. But it's the same thing. It's just different, writing it with different hands. So here, each mathematical trick corresponds to a code optimization, and there's one thing called a summing factor. And the final answer is that the number of comparisons used is n plus 1 times twice the n plus first harmonic number. H sub n is 1 plus a half plus a third plus a quarter plus up to 1 over n. So this nth harmonic number, minus 2n, is about 1.386 n log n. Einstein encouraged us to make everything as simple as possible, but no simpler. If you want to find the exact runtime of the algorithm, that's about as simple as possible. That's a little bit simpler, but it loses something. You can say it's proportional to n log n. Questions about that? Okay. I made you suffer through one analysis. But the good news is, but wait, there's more. You just saw not only an analysis of Quicksort, you saw an analysis of binary search trees. Why is that? If I show you both the order-preserving Quicksort, and again, randomization says that they're all alike, and I compare it to binary search trees, if I put the elements in this order, 31, 41, 59, 26, 53, the first element goes there, second element goes there, 59 goes there, 26 goes there. This binary search tree is strongly isomorphic. It makes not only the same number of comparisons, it makes exactly the same set of comparisons. So the analysis I just showed you applies not only to Quicksort, but to inserting random elements into a binary search tree. 2 for the price of 1. Complete analysis of search costs on the average for Quicksort and binary search trees, a sequence of transformations, a continuum from code to mathematics. There's an old line that if architecture is frozen music, then Stanford is frozen John Philip Sousa. In the same sense that data structures are frozen algorithms, you get a 2 for the price of 1. Where's the code? Well, in the book, I describe in some detail how I never really wrote the code. I played with it, I wrote it out on paper, but I never compiled it, I never tested it. At the very end, I took the final one, put it into a spreadsheet, and I got the right answers. I spent enough time in the Unix room to realize that you should not speak in public about code that you haven't really beat on, because someone else can just take it back on and beat on it once and make you look really, really silly. It might happen. But I've never written this code. I'm going to keep it that way. It should sometimes be seen as a soap bubble. That's the end of number 2. Questions about that? Yeah?
I have a question about your use of pseudocode. Is your definition of pseudocode that you drop the semicolons and the curly braces?
I'm trying to think if there are any other exceptions. Well, and I don't need to declare functions well either. Yeah, but pretty much that. Yeah. Yeah, and again, this is something that as a point of honor, I didn't want to write the program. I wanted to make it close. Could I translate that into a program that worked properly? Other questions? So throughout the paper, I have all these different aphorisms about simplicity. It's good, but it's not necessarily good at that level of detail. Yeah, what I just showed you is cute. It probably hasn't killed you to waste 40 minutes so far. Maybe even inspirational. Civil engineers can admire balsa wood bridges. When I worked at Carnegie Mellon, it was so cool to see the engineers, as we call them, the real engineers, walking around with these cool little balsa wood models that they put on things and put a big bucket full and see how much water they could support in it. That's cool. Some of us sat in the audience and heard Macready talk about the Gossamer Condor, a tiny little thing, really inspirational, really cool, but does it work in the real world? So I'm going to talk about the C library Qsort. Who already knows way more than they want to know about the C library Qsort? Who has never heard of the C library Qsort? Okay. So back in the day, before youngsters like Eric Gross were even born, there was this beautiful library function for its time with a less than optimal name. It should have been an array sort or whatever, but it was called inappropriately Qsort because it was based on Quicksort. If you want to sort integers, you define an integer comparison function, and you call the Qsort by saying, I want to sort this array A of integers. I have to cast it to that. There are this many of it. Each one is that big, and here's a function that compares the two. If you want to do it for fixed length strings, it does that. It usually runs an inlog in time. Here's a beautiful bug report. Wilkes and Becker sent me some email. We find that Qsort is invariably slow. That's a bug report. It's not beautiful. Not particularly beautiful. That's a pretty darn good-looking bug report. It's slow on organ pipe inputs like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, line 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah.
So before you move on, there was another really foul, evil bug on the previous slide. You are going to talk about it, aren't you? The fact that income does not work.
Exactly. It doesn't work for certain obvious reasons, yeah. If the numbers are big, and in the summer of 1974, I spent 2 very, very long nights debugging that on a machine with 16-bit integers. There's a horrible, nasty, insidious bug that doesn't work. It usually works as long as things are in the range, but don't most of us work as long as our inputs are in the appropriate range? No, it's only when we get stressed out. But yeah, there is an insidious bug there. Well, I or somebody smarter than I will talk about that soon, or before. Beautiful bug report. That's okay, pretty good looking. This is great. Here's a beautiful bug report. Here's a little program that will run through, it snarfs in from the argument line, it fills the array, and then it calls it to sort of the element of size 2 times n. And furthermore, here are the timings. What do those timings tell you? Yeah. So this is clearly quadratic behavior. Each time we double the input size, the runtime goes up by a factor of 4. So this whole thing, I will argue, is an amazingly wonderful, truly beautiful bug report that contains a succinct and beautiful bug report and a little experiment, a tiny little experiment that really shows that things are failing miserably. For my second experiment, I wanted to see how bad it was failing, so I added these lines to the code, exactly what I did before. Increment the comparisons by, at every comparison, start off at 0, print it out afterwards. Here, for 1,000 elements, sorting 2,000 elements takes exactly 1,000,000 comparisons. Wait 1 second here. As we say in the math business, definition, theorem, proof. I mean, it's just, 3 data points, hang the bastard. It's there. And in fact, what we did was we then ran some algorithm animation to show exactly why. That showed you how to phrase the loop invariant. You could prove it that it does not randomize, but rather chooses the middle element. The combination of the partition element and the code together leave the shape invariant. And if you run the animation, you could just see how this thing left enough shape invariant, and you could put the statements in and prove it. So at this point, in the early 90s, Doug McElroy and I set out to replace a veteran of about 2 decades experience. It's a little bit humbling to take some code that's been around there for since the late 60s, early 70s, and try to replace it. Our strategy was to start simple, add only essential things, use known technology, and then just test the bejesus out of everything. Just test as much as we could. Correctness, profiling, do cost models, all these torture tests to throw as many bizarre shapes at it to see if it was well behaved. We started off by taking the code I showed you before, the 2-pointer scanner code, converted it into this model. It's not all that obscenely ugly. I didn't really understand it, but I've lived most of my life not understanding things. I can cope with that. We did a field test on it. It was based on the classical algorithms, about 20 lines of code. The Broken Qsort one was 5 times as big. Ours was faster and fairly robust. It doesn't die on anything we noticed. This is pretty reasonable. However, on all equal elements, again, this will gruntle you greatly. On all equal elements, the old Qsort takes linear time. Ours took n log n time. A vigorous, interesting, incredibly helpful user by the name of Tom Duff said, bastards. We said, no. We said, you don't understand. We provide predictability. What we're giving you here, what we're offering you at no additional charge, is complete. Ours always takes n log n. The other one, it shouldn't take. He said, no. People sort to bring together equal elements. They do it all the time. You're making it run way slower on a really common class of inputs. You can't do that. Well, he's a large guy and a mean guy, so we couldn't do it. So what happens on equal elements? Some quicksorts go quadratic, the one I showed you. Some use exactly n log n. That's better. But some use linear time, and particularly the broken element did. And I think a really interesting problem is there a really succinct element that gives you linear time on equal elements? It's sort of fun. So could you do a fast algorithm for ternary partitioning? Well, people have been thinking about this for a long time, like since the early 60s. And they can do this. So the classic algorithm was, well, you divide it into less than over here, greater than over there. The equals come sort of there. But if I have 3 or 4 equals, what ends up happening is that the 3 or 4 equal guys have to sort of roll over like a tank tread, having each one go over in the middle, and it really slows things down. Is there a way that I can get around that? Well, we thought about that, and it turns out what seemed more natural to us was the following. This was sort of an aha moment. Rather than having them roll over like a tank tread, if I find an equal element, I'll just stick it over to one side. I'll stick all the equal ones there. Whenever I find an equal one, I'll put it there. At the end, what do I do? Well, I'll swap them back to the middle. That'll be cool. This will give me most of the speed, but the code still wasn't beautiful. Why is that code not beautiful? It's something that all of you have been genetically programmed for the past hundreds of millions of years to really like a lot. What does that program not have that all of us like a lot? Symmetry. I mean, we had this deep genetic programming to really enjoy symmetry. And so if I make it like this, it becomes less ugly. And the final state will be like that, so I can just swap these things back. If I do that, I get to this code. That code is not subtle code, but it has the 4 pointers I showed you before. It's pretty straightforward. It's fast. It has a lot of properties. At the end, you swap back as many as you need to. Sort of reasonable. That gave us our baseline code. It was sort of a new partitioning algorithm. Got the baseline there. What do we do? If you have algorithms, they teach things like, well, the first thing you want to do is make a handmade stack. Only wussies use built-in recursion. Manly men, real stupid men, always go for their own handmade stacks. Guy Steele has a great quote about if the user can do it faster than the machine implements it, then the compiler writer has blown it badly. Well, you insertion sort small files. Well, not just insertion sort. Any wussy can you do binary insertion sort. You do the smaller subarray first. That way you'll bind it down to log n size. You sample to choose a good partition element. You do sentinels. You tune the loops. There are all these things you can do. Many of you have had classes, algorithms classes. let me rephrase that. Many of you who have had algorithms classes have studied Quicksort, and you've seen all these things where they just sort of pile on these traditional things. And if you're working in mix, boy, it's exactly the right thing to do. How many people here write in mix on a regular day? 2009, if anything, I trust. MMix. How do you choose which ones to do? Well, what we did was a whole bunch of experiments, runtimes or implementations, and a whole bunch of simple cost models. I'm not going to give the details, but we did things like saying ballpark, here's a cost model, run a simple program. On this machine at this time, integer operations took that much time, pointers took that much time, control structures took that much time. All of these comparison functions took an order of magnitude more. What was really surprising was that our swap function took about another order of magnitude more. Why was swap so outrageously long? Well, swap did it char-wise. It just swapped each character as you went along, and it would write back into things. Whereas, in fact, if you did it with a bit more cleverness, if I swap 2 ints, I get an order of magnitude speed up. So by doing a simple cost model, what ballpark do things run in, we learned a lot. Swap is really expensive. We swapped intwise when we can, charwise when you must. We hit that all in macros. The canonical model that Knuth introduced in the 70s, and people kept with it for at least a quarter century beyond when it was appropriate, said that overhead and comparisons are the same, swaps are what really kills you. We found out that if you do swaps properly, comparisons are where we should focus, so we did focus on that. We found that choosing a partition element was really important. The typical one of the first or the middle or random gives you about 1.4 in log n. Median of 3 beats it down to 1.2 in log n. We used a variation of what John Tukey called a ninether, about 1.1 in log n. We reduced the overhead from 40% to 10%. We insertion sorted small files, nothing fancy, a simple insertion sort. That was a pretty big win. So we had these things in here. We left out all of these things. It wasn't prudent to do your own handmade stack. We didn't want to sort the smaller subarray first. No sentinels. We couldn't do it for certain technical reasons. No binary insertion sort. Gordon Bell has a lovely observation that the cheapest, fastest, and most reliable components of a computer system are those that aren't there. And it was certainly the case that the cheapest, fastest, most reliable components of our sort were the ones that never went in there. Yeah.
So, a quick question, which is the binary insertion sort is n log n comparisons for quadratic motion. If comparisons are what really kill you, then why didn't you try the binary?
Oh, we could have tried it, but it only gets down, we only use it when n is less than 8 or 10. Yeah. So it's only for very small values, and you can reduce it, but it's too much overhead and just didn't seem worth it. Here's our complete code. And the code consists of, here's the swap macro, here's this adaptive partitioning here and here, here's the final insertion sort, here's the clever partitioning. So just take what matters and use it. When you did this, it was inspired by a real problem. It was the world champion in 1991. I'm on the paper of some applied algorithms conferences, or on the program committee of conferences, and people often still choose this as the one to compare it to. We did some nice theory along the way and came up with a new tool that led itself to some other interesting algorithms. Some beauties of Qsort. I wanted to talk today, to waste your time, just to think about the beautiful code that you've written. And thinking about this, what are some things here that have done this? I'm telling you about work that people have been thinking about for 45 years, a beautiful algorithm. I had the pleasure of discussing this with Tony Hoare at one point, and he pointed out when he did Quicksort, he wasn't going to publish it. It wasn't big enough to publish. He only decided to publish it when he could do the mathematical analysis of it. And he wrote this wonderful article in the Computer Journal. The interface, the Qsort interface, is very nice. The bug report I really like. People know how to do a succinct, beautiful experiment. It's wonderful. These cost models, it's the swap stupid. Now it's the comparison, just knowing what the models are. Our correctness tests and the time torture tests were nice. And then I like the beautiful sequence of functions in both cases. Many of us do that. We start with the program and we make it better and better and better in these logical steps. But as you get to step 12, is step 6 really still relevant? How can I think about this, go back and do things in this systematic way? So I've tried to show you some beauties. A question for you is, what's the most beautiful code that you've ever written? It was really fun for me to think about, and there are different answers. So if I were to ask, what's the simplest implementation of a potentially nasty function with a correctness proof? It's almost right. Almost. I might have one answer. If I ask, what's the most devilishly clever speed hack I've ever done? Or what's the most beautiful extension of an old idea into a new domain? In these cases, it would all be some variant of binary search. So it's a binary search in which Josh recently found a really interesting subtlety. A subtlety in the sense of, when you fall down and smack your face in the road, you say, there's a big subtlety on my forehead. A loop unrolled binary search is pretty cool. And generalizing binary search into two-space and beyond and multidimensional binary search trees. So there's some clusters here. So I encourage you, I found it very worthwhile to think about what's the most beautiful code that I've written. I encourage you to do the same. What are your questions? What are your answers? There's some references there. What I've talked about here are 3 beautiful quicksorts, I hope. The first is just a simple teaching tool, a dozen lines of code. The second is trying to make the point, I think this is the most important point, about adding function by deleting code. That's something where I tried to tell this little tiny story. In real stories, you can sort of hear it. You talk about it around the lunch table, where you get these things where it really makes a big difference. The action there is not in dozen-line programs. I illustrated it for concreteness with the dozen-line programs, get it down to 0, and made a continuum from code to mathematics. But the real thing is adding function by deleting code. And finally, I gave you a brief history of an industrial strength Qsort that seems to have made a difference. Parting platitudes: strive to add function by deleting code, and make everything as simple as possible, but no simpler. I wanted to stop when the big hand was right in front of the 12, and the big hand right now is pretty near the 12. Any questions? Anything else we want to?
Okay, so I'm sorry, but 3 things. Thing 1 is that your Qsort code is actually really widely used. You're being modest when you say it's still kind of widely used. In addition to the fact that it's still in a lot of Unix platforms, it's also the standard primitive sort in Java. That I just took John's code and stole it, but I did give him credit. Second thing is, you said the Qsort is kind of a beautiful interface. I actually quibble with that because the tri-value comparison function is error-prone and it pushes you towards Quicksort when maybe you really want to use merge sort. It would be cheaper to have a 2-value, just less than or equal to or not, actually less than or not, if you're doing merge sort. So I'm sorry that in Java I didn't allow that choice. Oh, and finally, this business about the simple as possible but no simpler, I don't believe Einstein said it. I actually have spent maybe 20 hours trying to find out whether
I live for moments like this. Number 1, thank you. Number 2, you're right, dead on, I agree. Number 3, my boss now is a guy named Dave Weiss, who was talking about someone at SRI and saying the same thing about, did Einstein ever say it? And this guy at SRI said, well, I think he said it because I heard him say it. So I don't know if it's ever written, but at least I can give you the back pointer to my boss, Dave Weiss. And if you send to weiss@avaya.com, he can give you the name of the person that said, I think Einstein said it because I heard him say it.
So I actually had someone at the Library of Congress research it for me, and it's not in print.
Yeah, and again, that's totally consistent with this, but weiss@avaya.com had this wonderful story. So, boy, a comment like that's going to be hard to follow, but thank you, yes, maybe. I don't know. Anything else? Thanks.